Q. So okay, other thing is always okay holding the top of the step address value. So this is some definitions for the what meaning okay the R13 okay holding the data. So let's say okay this is representing a group of the step. Okay, so when the data is writing into the step, okay, the process is called push. Okay, to take the data, to read the data from the step and then take up here, okay, into another some locations like maybe into the register. In this case, okay, this process is called pop. Okay, so the instruction is similar. Okay, later you see, okay, the pop, okay, process, okay, is defined, okay, inside a program defined using the mnemonic POP. Okay, and then the push process K is indicating K by using the mnemonic PUSH push. Okay, so the step pointer is always K pointing to the top of the step. Okay, so okay, let's say this is okay, if this is representing the top of the step, so the step pointer always pointing to this address value. So the SP is pointing, holding the address for this memory, step memory. Okay, address is not okay the content. So this diagram illustrate the concept okay of the push and pop process. Okay, which okay associated to okay storing the data into the step memory or reading the data okay from the step memory. Okay, so far so good. So okay, until this point, okay, you learn two new terminology, which is push and pop. All right. Okay, push okay is to store the data into the step memory. Pop okay is to read the data from the step memory into case and general purpose register or into certain locations. But in ARM normally is okay read okay and then move to the general purpose register. All right. So this is one example okay illustrate the push and pop okay process. Okay, so okay in this coding there is some mistake. Okay, so actually there is some mistake on this address for the step pointer. Okay, so the two actually is one. Okay, one actually is two. So the address actually is for the step pointer is a 0x100000200. Okay, so this is referring to the in the when you in the programming afterward. Okay, but in this lecture not, since it is already okay got some typo error, so the discussions will be just based on we assume okay this is the step okay top of the step okay address okay for the step. Okay, but actually okay this is the real one okay the correct one, this one is a wrong one, but our discussions were using this one. Okay, so okay first of all okay inside the program we know that okay we need to access to the step memory. Okay, so how to access to the step memory, we need to know what is the top of the step address. Okay, top of the step address, okay, let's say this is the top of the step address. So okay we need to define okay and then assign this to a parameter first. Okay, so okay to do so okay you can use a directive okay equate okay to assign okay this value to the stk underscore ad variable. Okay, so then after that inside okay the following programming okay it is possible to using this label to represent this figure. There's a purpose for the directive, equate directive. Okay, in the following instructions, this is to assign the address, this address value. This is a label, right? So now this label already assign equivalent to this this figure, so which is representing the top of the stack address. So in the following line, we need to log the top of the stack address information into the stack pointer. So this stack pointer is referring to R13. So in the programming, in case you need to assign the top of the stack address, then you need to declare these two instructions. So you will get SP at the end of this execution of these two instructions. The SP will equal to 0x 20000100. Okay, so that is after executing these two instructions. Then the following instructions, this is just to load the 32-bit data into the R0 register, and then to load these two 32-bit data into the R1 register. So just define a value assigned to the general purpose register. So from here, it is expected R0 will be equal to this after the executions of these two instructions. So R1 equals to 1A, 2A, 3A, 4A. So this is after execute these two instructions. So R0 contain this, R1 contain this. Then if you look at the next instruction is push. Push and then hairy bracket. Inside the hairy bracket, it define the general purpose register R0 here. So this means that the content, the whole 32-bit content for the R0 will be pushed into the step. So the command behind here, this is to push R0 to top of the step. So what is the result? Later they will in the following slide got some diagram that illustrate the result. So typically this value will be pushed into the step stick to the little endian format. So it is also stick to the little data will be arranged in this little endian format. So what is the meaning of the little endian format? That means R0. If you refer here, R0 right now here, it contains 32-bit data. So 32-bit data, if you divide 10, it actually is a combination of 4 bytes. So 7 X, this is a byte. Actually is a representing the byte 0 in this case. Byte 0. 56 in this case is known as a byte 1. 34 in this case, we know that is referring to the byte 2. 12 in this case is referring as a byte 3. So little endian format means that the lower byte will be stored at the lower address. So inside right now the step memory start from this address, top of the step. So let's say the top of the step right now is a 0x20000100. Let me change the color to say to pink. So this is the top of the step. This is known as a top of the step. Okay, TOS, top of the step. Okay, so when the data, okay, when implement these push instructions, okay, in the step, okay, it will actually the data is not so in the address increments sequence. Okay, it will reduce, okay, the address, okay, by 1 and then start to set the data. Okay, so that means, okay, the first byte of data, okay, it will be 1 2. Okay, this will decrement by 1. So in this case, okay, when this address decrement by 1, okay, it is expected, okay, to have 0x2 0 0 0 0 0 FF. So this is the, okay, address, okay, after minus this by 1. Okay, so what, when you minus this address again by 1, okay, so the address value is 0 x2 0 0 0 0 0 k fe. Okay, so again you minus this address, okay, by 1, you will reduce, okay, become 0 x2 0 0 0 0 0 0 fkd. Okay, and then again, when you minus by 1 again, this address, then the K address value becomes 0x2 0 0 0 0 0 FC. Okay, so now this K 4 byte data, okay, will be stored, okay, inside, okay, these 4 addresses. Okay, okay, just now, okay, I mentioned that, okay, one address, okay, one memory cell, okay, normally will be assigned one address. So that means this address, okay, only has a cell, a memory cell, and then this memory cell only store a byte of data. Okay, so this, okay, memory cell also store a byte of data. So this one also store a byte of data. Then this one also store a byte of data. So in this case, okay, to store 32-bit data, it requires 4 memory cells. So in this case, okay, these are the 4 memory cells, okay, that, okay, will be stored this data. But how the data organized and stored inside the step, okay, it will, okay, stick to this little endian format. And then in the little endian format, okay, it mentions that the lower byte will be stored at the lower address. So when you analyze in these 4 addresses, okay, which one is a lower address? Okay, anyone can tell me? FF, FE, FT, or FC? Which one representing the lowest address?
FC.
FC, right? Okay, so that means 7X will be stored at the address FC. Okay, so then the following subsequent byte 156 will be stored at the address FT. Okay, so this is a 56. Okay, and then 34 will be stored, okay, at the address KFE. Okay, and then 12 will be stored at the address FF. Okay, so, okay, this is the, okay, actual storage, okay, how the data being stored inside the step. But in the step memory, okay, normally what we define, okay, we will define in the size of 32-bit instead of like this, 8-bit. Okay, so, okay, when you look at the following figure, okay, what you see is, okay, you only see this address being given and the top of the step, okay, which is pointing to, okay, before before execute the push, okay, this is the top of the step, right? Okay, but after execute this push, okay, this 4 byte data, okay, already, okay, stored inside the step. So this time the top of the step is referring to this, okay, address. Okay, so this become the top of the step. So that means the top of the step, it will change, okay, best case from time to time due to the operations. So this is become the top of the step. But inside, okay, the following slide, okay, if you look at here, they were organized in the byte size. Okay, so which is start from this, okay, and then in the next, okay, cell here, this actually is to store 32-bit data, but okay, it show the top of the step, which is FC. Okay, then after that, -4, okay, which is, okay, the following, the subsequent top of the stack is F8. And then, okay, -4 again, okay, the subsequent top of the stack is F4. So, okay, this is the sequence of data being, okay, it behave like the data memory address behavior, okay, in the step. So it is not, okay, operating in the increment mode, but it is in the decrement mode. Okay, so it starts from the, okay, largest address value, and then you will see it getting smaller and smaller. Okay, if, okay, there is a push process. Okay, and then when there is a pop process, the address value will increment. All right, so far, okay, do you clear of this? So when
tadi doktor kata pembetulan 0.100.
Ini, yes.
So
this is in the actual referring to the data sheet. Okay, the step pointers top of the step value actually is this. It's not this one. This is the wrong one. Mistake in the typing. Okay, actually this is 2, supposedly is 1. This one figure supposedly is 2. Okay, so to avoid confusions in the following discussions, we will stick on this value. But in the coming programming, okay, in the I think in the following chapter 4, okay, you must remember this is the actual top of the step value. Okay.
Okay, thank you.
Okay, so okay, we come back to here. Okay, so in the step, okay, the data will be arranged in 32-bit size. So in this case, okay, when they are arranged in 32-bit size, okay, so that means, okay, they will be organized in after they combine, okay, what you will get is 0x, 7x, 5, 6, 3, 4, and 1, 2. Okay, this will be the data, okay, that appear inside the if in these organizations. Okay, so why, okay, you get these organizations? Because this is referring to the top of the step. Okay, even though here you see it seems like it's the is a upper byte lah. Okay, it's like this is a byte 4, but okay, actually due to these organizations, okay, so the memory cell supposedly it will start arrange, okay, FF as the lower byte lah. Okay, then followed by this, and this. Okay, that's why you get this, okay, arrangement, okay, in the 32 bits size. Okay, instead of the 1, 2, 3, 4, 5, 6, 7, 8. Okay, clear? Okay, so the first push, okay, it will push, okay, R0 into here. Then next, okay, when executing the next, okay, push process, okay, the R1 value is referring to this. This is the R1 value. So this value will be, okay, pushed into the, that means FC will be reduced again. So you can reduce by one, okay, get 4 byte, okay, and then after that, okay, lower byte, okay, store 4A, okay, then after that, okay, the next byte, okay, store next cell storing 3A, 2A, and 1A lah, organized slowly like this. Okay, then you will get, okay, the top of the step, okay, is a FC. Okay, the top of the step is a no, not FC lah, F8. Okay, which is okay, here. Okay, the value R1 value will be pushed into here. Okay, and then at this point, okay, the top of the step is a 20000 F8. So okay, once K finish, okay, then the following sequence instructions, if you look at here, okay, organize, okay, with the pop instructions. So in this case, the pop instruction, it will pop up the top of the step value. Okay, top of the step value just now is, okay, referring to R1, right? R1 value push in last. So it will, okay, pop up first. Okay. So, okay, the R1 value will be popped and then saved inside the R2. Okay, then the following pop instructions, okay, it will pop this value, okay, into the R2. So actually you can, okay, run this, okay, by using the Kai microvisions, but this sequence of instructions not yet completed with the defining the directive. So you need to complete, okay, the directive, so that when you run it, you don't have the error. Okay, if you just run this sequence of coding, okay, you won't get the result. Okay, because the program is incomplete. But when you run in the Kai microvisions, in this time, okay, you need to change this. Okay, replace it with this address value. You need to replace with this value. This is the correct one. Okay, clear? Got what I mean?
Yes, okay.
So the following slide actually is descriptions on the process, okay, in the sequence given in this example. Okay, explain okay, what happens, okay, one by one. Actually, I explained just now. Okay, so this is I explained in the slide so that, okay, you can refer to the complete program. Okay, this is a sequence of program. In the following slide, they break into the several pages. Maybe you'll get lost. Okay, but for, okay, self-study, it is very good. Okay, you can spend time to understand, okay, the slide, okay, and then to get know, okay, what happens from one process to next process. Okay, so first, okay, this slide is showing, okay, after execute these 4 instructions, what happened? Okay, what are some changes in the what happens inside several register or the step memory. Okay, so first, okay, the first is to assign, okay, the top of the step to the label, okay, stk underscore ad. Then after that, assign to the sp. So these 2 instructions, okay, it will affect here. Okay, it define the step, okay, top of the step best address. Okay, so that means the top of the step, okay, it will, okay, define starting from this point. Okay, then, okay, the following 2 instructions, these 2 instructions, it will initiate, okay, the data, okay, inside the R0 register and R1 register. So, okay, after executions, okay, this will be some finding, okay, outputs, okay, result. So R0 contain this data, okay, R1 contain this data. Okay, clear? And then at this point, okay, the step register contain nothing lah, because it just starting to define the best address for the top of the step. Okay, so next, okay, in the coding, okay, it execute the push, right? So push, okay, push R0. So R0 initially contain, okay, this defined already, right? So it contain this. So in this case, this 32 bit value, K will be push K into the step memory, start from here, top of the step. So the data will not store at this the top of the step address. It will decrement by 1 first, okay, and then start from here. So in this case, okay, this will be the address, okay, referring to FF. Okay, FF address, okay, and then 34 is okay, referring to the address FE. Okay, so 56, okay, will be stored at the address FD. Okay, 7X will be stored at the address FC. So which is, okay, because in this case, 7X is referring as a lower byte. So it will be stored at the lower address. Okay, and then due to the organizations, they are organized in the decrements, okay, decrement form. Okay, so okay, the 7X, okay, the lower address is located at this point lah, instead of here. Okay, therefore you will get some arrangement like this, like opposite, okay, to the content of R0. All right, clear, right? Okay, then next, okay, the push R1. So push R1, okay, will be push this data. So this is the data. So this is the input, okay, and then push, okay, start from this. Just now is from previous executions, top of the step is referring to FC, right? So, okay, to store the data, okay, when execute this push, okay, so FC will -1. So this time is okay, FKB. So FB is referring to these positions. So this is okay, FB. Okay, then this is F, refer as FA. So, and then this is referring to the F9. Okay, this refer to the address FX. Okay, so, okay, so this is the higher address. This is the lowest address. Okay, in this top of the stack lah, in this 32 bits. Okay, four memory cell, step memory cell. So, okay, FX, since it's a lower address, so the lower byte for A will be stored here. Okay, the subsequent data 3A will be stored at the F9. So 2A stored at the 2A, FA here, these locations, and then 1A will be stored at the address FB. Okay, so therefore, okay, this will be the result. All right, clear?
Okay, doctor.
So it's clear. So let's proceed. Okay, so next, okay, is the instructions given, instruction pop. So pop, okay, it will, okay, read the data, means take the data from here, okay, and then move into the R2, into the general purpose register. Okay, so again, okay, the data transfer, okay, will still stick to the little endian format. Okay, so little endian format, lower address data, okay, will be stored as a lower byte. Okay, so in this case, 4A, okay, this is the top of the step, okay, from the previous slide. This is the top of the step. So that means this is the data will be pop up, okay, in this executions. So this data, okay, will pop into the R2. So how they are pop up? So according to the arrangement of the data, okay, inside the memory cell. So 4A is referring to the lower address, the lowest one, FX. And then this is the F9. So this is FX. Okay, so F9. Okay, FA and FB. Okay, so lower address content for A, K content will be move to the lower byte. So this is the position for the lower byte. So the data for A place here. Then 3A, place next to the 4A. So these positions. Then 2A, place at these positions, and 1A, place at these positions. So after pop out, when you compare to R1, their organizations is the same. But when compared to the data organizations inside the step, they are in the reverse form. But in a group of byte. So this is the some hints for you to do the checking. So is the data organizations inside the step, is it correct or not? So next pop instructions, it will pop out the data start from the top of the step, which is FC here. So this is the content. So the data will be popped to R2. So that means previously it contains some data. And then when execute the pop R2 again, the new data will replace the content of the old data. So all data will disappear. So at this point, similar, the data transfer out will stick to the liter endian format. So 7X, this is referring to the address FC. In this case, 56 is stored at the memory cell address FD. 34 stored at the step memory cell FE. 12 is referring to the memory cell address FF. So in this case, 7X is considered as the lower byte. Followed by 563412. So after pop, this will be the result. So any inquiry on this push and pop process, and then the data arrangement inside the step memory. Any questions, class?
No, doctor.
So hopefully you understand. So if understand, let's continue. So next is what is the subroutine? So the step memory discussions, the relations to the step pointer content. That's all. These are the parts that we'll cover. But after this, you need to do the revisions and make sure you understand the principle, work principle for the step. Because normally in the exam, there's not many theoretical questions. It is more on the activities one, like hands-on, practicals questions, some kind like this. Ask you to find, determine the content, for inside the step memory, and then after the execute, what is the content for R2, some kind like that. So the last part is the subroutine. Subroutine is the most large program consists of many smaller blocks of code. So subroutine normally inside a program you can insert many subroutine. So every subroutine contains some sequence of instructions. So this sequence of instructions, you will perform some tasks, which is maybe specific for one process. So it is known as a subroutine, where function can be called at will, such as a plain routine or a complicated arithmetic functions like logarithm. Okay, so okay, what you going to put inside the subroutine, okay, is up to the programmer. Okay, maybe sometimes it performs some arithmetic function, or maybe it's to perform some specific algorithms. Okay, so in this case, you can arrange, put them inside a subroutine. Then after that, this subroutine can be called, when it is needed. Okay, a large task can be described more easily in this way. So subroutine, it will make complicated programming, or program, become easy to manage. Okay, because the subroutine can be tested, one by one. Okay, if you combine everything inside a large program and then you perform a test, okay, at that particular time you might encounter lots of problems, okay, or maybe errors, or maybe when you encounter some functionalities problems, you have no idea, okay, where supposedly to fix the problems. So there is a difficulty of managing a large program. So the practices in handling the large program is, we break them into smaller coding called subroutine. So subroutine also allows programmer to write and test more block of code first. So this is the advantage. Okay, we break them into a group, certain tasks. Then after that, write a sequence of program, and then we can perform a test on this sequence of program. Make sure they are correct. It can work according to the desired specifications. So once test everything done, then you can proceed to the following parts to solve the problems. So the problems will be solved one by one. So will be test and then building on the knowledge that they haven't been proven to work. Okay, so this is the one of the advantage. Okay, subroutine is called with the BL. This is an acronym, branch and link instructions. So in the instructions, you will call it by using the mnemonic BL. And then this representing branch and link. These instructions transfer the branch target. Normally is referring to the starting address of the subroutine. So the BL, it will point to the starting address of the subroutine. Okay, and then this address will be loaded into the program counter and also transfer the return address. The return address is before leaving. When encounter the BL instructions, supposedly the PC pointing to the address of the subsequent instructions. But since the CPU will perform the branch and link, that means it will leaving from this point. So the subsequent locations of the instructions, the address will be stored inside the link register. So and then there will be react as a return address after complete execute the subroutine. So that's why there's a mention here transfer the return address into the link register. Still remember inside the programmer model, there is a register R14 dedicated as a link register. And then from the general description, we know that link register is to store the return address. So when dealing with the subroutine, so at this time, there will be some relationship to the link register R14, so that the subroutine can return to the calling program. So it will back after finish execute the instruction inside the subroutine. So it is also possible to call the subroutine from another subroutine. So, okay, for example, okay, when you are inside a subroutine, you can also call another subroutine from the subroutine. That is possible, but you need to handle it, okay, with care, because okay, there is a, we know that there is a information of return address, right? So when you call a subroutine inside a subroutine, so actually, okay, the link register contains a return address. So this return address, okay, must store first in somewhere else. If you don't store this return address, later in the following calling of the subroutine, the new return address will replace, okay, the old return address value. So when you, okay, after finish, okay, calling the subroutine inside a subroutine, okay, it will back to into the subroutine, right? Then after execute instruction inside the subroutine, it must back to the main program. But since the data is disappear, just now you don't store it, so there is no way to go back. So it will, okay, cause some execution halt, okay, fault inside the CPU. So that's why, okay, if you like to create some program, okay, that contain the operation calling subroutine from the subroutine, okay, you must ensure that, okay, the return address informations must store, okay, in first before calling another subroutine. So this, okay, you can get this idea afterward. There's one example, okay, calling the subroutine inside subroutine. So here, this is an example for the subroutine, calling subroutine only. Not this example lah. Okay, calling subroutine from subroutine later I demonstrate by using the another, okay, another coding. So let's look at the subroutine example first. Okay, so in this example coding here, okay, if you look at here, this is the program for main body. So this is referring to the, this is main body, sorry. So this is all right, okay, never mind. Okay, we just look at here. Is there any circle? A circle around. But circle around, okay, it will disappear. I cannot open it. Oh, can. Okay, so the instructions, okay, inside the circle, this is a circle. Okay, so this is actually referring to the main program. Okay, so inside a main program, okay, if you analyze, okay, the instructions, okay, start from the LDR, okay, loading, defining initial value for R0, R1, okay, and then in the third instructions, there's a BL, branch and link, okay, instructions, okay, and then, okay, followed by the operands, okay, which is, okay, showing a label. So this label, okay, is referring to the label of subroutine here. This is a subroutine. Okay, so okay, this is a, we can indicate how we call the subroutine, okay, inside the main body. So inside main body here, okay, call the subroutine by using the BL instructions. So when the CPU encounter this, execute this instruction, it will point to here. So inside the subroutine itself, you can arrange sequence of instruction as well. But in the end of the subroutine, you need to include this instruction BS. BS instruction is the instructions to direct the CPU back to the main program. So the BS instructions is a mnemonic. Next, you need to define an operand. So the operands normally is referring to the LR operands. LR is a link register. So when you create these instructions, that means that the LR address value will push into the PC, so that the PC know to go back here, come back here. At this point, we encounter this, the PC, the program, actually the CPU, it will jump to here. Jump to here, execute here, and then start to execute instruction inside here, start from push and going down here. Then after that, encounter these instructions, and then the LR contain the return address. The return address, it will point, this return address will loaded into the program counter. So, the CPU know, come back to the main program and then start, continue the execution, start from the instruction LSL, here. So, the operations, call from divert into the new locations and then back to the main program. It works together with PC link register. So you need to know the relationship between these two registers. And then you must remember what are the functionality for these two registers. They play a very important role in the subroutine operation. All right, clear? Any questions? So far, so good, class.
Yes, doctor.
Okay. So maybe let's go to the following slide to look further lah. So in the following slide got some figure to explain the process. So first we look at how the microprocessor execute the instructions. So the initial value in the register and the step just before execute the BL routine 1 instructions. That means it's referring to here. In the first 3 instructions, it will result. This will be the result. So R0 defined with some initial value. R1 defines some initial value. And then PC, it will pointing to some locations. The locations which is referring to the here lah. Before execute the BL lah. BL instruction. So PC will pointing to here, BL. SP will contain this, which is showing the best address for the step memory. So pointing to these locations. So the PC initially contain this, which is point to the address for the BL instructions. Branch before branching. So when execute the branch BL routine 1, this value it will increment based on the size of the instructions. So after execute the BL routine 1, so the subsequent address, subsequent address is referring to the address for LSL. The address for LSL will be pushed into the link register, because when execute these instructions, the PC okay, will point to this address, okay, which is referring to the name label routine 1. So PC holding new address value, which is 418 in this case. Okay, and then the subsequent instruction address will be pushed into the LR register. So, okay, so this LR register content normally is the address value. Okay, there will be some increment, okay, in +1. So LR value is loaded with return address +1. So in the actual executions implementations, the return address value, okay, +1 will be stored inside the LR register. So PC point to the routine 1 address. Okay, and then step, okay, base address still the same because the instructions does not have any impact on the step pointer, so no changes. Okay, and then no relations to the general purpose register, so they remain no change. Okay, then next is the execution of push. Okay, push R0 R1. Okay, we come to here. Okay, when come to here in the subroutine, the first instruction is push. Okay, R0 R1. This is actually storing the original data inside the R0 and R1 because in the following executions, it will cause some changes inside the content for the R0 and R1. Therefore, we need to remain the data, original data inside the R0, R1. So one approach is we can save the data inside the step memory. So that's why the push instruction is included, defined as the first instruction inside the subroutine. So the push instructions will push these two data going into the step. So the data stored inside the step memory. Then after that, the following two instructions will move the data into R0, and then to perform some subtractions and then store the result inside the R1. So it causes some changes inside the content of R0 and R1. So if we don't save this original data, so this data will disappear. Then before leaving from the subroutine, as a programmer, you must have a very clear mind. Just now there is some data, original data inside the R0 and R1. So when before going back to the main body, so what you need to do is to pop up the data, and then to reset up the content of R0 and R1 so that when returned to the main body, the contents inside here remain no change, still the same like before leaving. So this instruction must added before the BX instructions. So the BX when execute the BX instructions, it will instruct the CPU to take this value, the value inside the link register -1, and then restore back into the PC. So this value will store inside here into the PC. But there is a little processing which is you will perform LR -1 and then after that store inside the PC. So this is the location, exact locations inside the main body whereby the CPU should go back. So this is some things that are happening inside the CPU during the executions. So when you do some analysis, you will require a clear mind, and then a very firm understanding on the principle. All right. So that's why from the beginning, I keep on reminding you, okay, you must do revisions. So clear? Any inquiry? If no inquiry, I will proceed subroutine to subroutine. Then we try one example in the test paper. Okay? Any questions?
No, Doctor.
No. Okay, so let's complete this. Okay, nested subroutine is actually a implementation of call a subroutine from a subroutine. Okay. In the previous example, there's only one subroutine. Okay, hence only one return address is needed to be kept track. Okay, however, if you need to call another subroutine from a subroutine, so there will be two return addresses that need to be saved. So you cannot simply save in the same link register. So in this case, you need to arrange. There are some way to arrange to manage it. Therefore, BX instruction cannot be used in this case. Can be used, but only used in the last call of the subroutine. So in the nested subroutine, the stack is used to store the value of LR, as shown in the following example. So like this. So this is a program. So if you look at this program, it contains a main body. So this is a main program. This is a routine 1, the first subroutine. And then routine 2 is representing the second subroutine. So we go back to the main body. So in the main body, the beginning is to set up the SP R0 value, R1 value. And then there's a call of subroutine. So call routine 1. So when call routine 1, the CPU will jump to here. So that means the return address to move to execute this instruction will store inside the link register. So when calling the subroutine going into the subroutine here, you know that if you analyze the subroutine routine 1, there's a call to the subroutine again. So that means it will it will have some calling nested subroutine, call the subroutine from the subroutine. So that means when execute this call subroutine, the new return address will push into the LR register. So therefore, before calling the subroutine, the first thing you need to push the LR value into the step. So in other words, we need to store the return address inside the step memory first. Then right after that, you can doing some processing and then call for the subroutine. So when call to the subroutine, routine 2, this is actually referring to the second subroutine. So in the second subroutine, you no longer need to save the LR register content because there is no calling subroutine inside this subroutine. So you can just remain the LR content, the return address inside the LR register. So so that when finish execute this subroutine and encounter the BX instructions, then it will back to the back into the port here to this position. So in the routine 1, because the return address stored inside the step. So this time, you can just simply pop the content of the step register into the PC, the step memory, the content of the step memory into the PC directly. So the CPU it will point to here. So come back here. Finally can now come back here. Due to the port process here. So all these requires the organizations from the programmer. So you need to know lah, okay, what happened inside the program, inside the CPU when you arrange a program like this. Okay, what will be the outcome? What is the effect? So some of the point you must remember that, and then implement inside the when writing the program. So that's all lah, our formal discussions on this chapter 3. So any questions about this calling subroutine from a subroutine? Okay, any inquiry, class? So any question, class? No questions.
No,
No,
Doctor.
Doctor.
Okay, so if no, so let's look at one of the I take one of the exam questions as the exercise for exercise purpose. So I take it from the author. So inside the authors, do you know that I got upload some of the test paper, past year test paper and final exam paper. You can download from the author. Okay, inside the past year questions tab. Okay. So I just take the test paper lah. Okay. So from here the first test paper. Okay, so I take it from here. So in this test paper, it contains some multiple choice question you can try on. Okay, so for you to familiar yourself, to strengthen your understanding in the fundamental, the topics that we discussed in the chapter 1 and chapter 2 and 3, and then to get familiar with pattern of the questions. So normally some kind like this, it will, maybe to test your understanding on the RISC and CISC, what the difference between these two architectures. And then what is your understanding on the microcontroller, and what are the differences between the microcontroller and microprocessor. Then test your understanding on the operations for the register, like program counter. So if you look at the questions 3, suppose that program counter which is referring to R15 contain this address. From what address would the context entry fetch instructions? So now the PC is pointing to this address, but we know that when the PC pointing to this address, actually the PC is not execute the instructions for this address, is execute the instruction before this address, but start from which address. So you need to know what is the size of the instructions. In this case, the instruction size is 16-bit wide, given here information. So that means this address must -2. Each address memory cell store a byte of data. So 16-bit wide means it requires 2 memory cell to store the 16-bit data. So the two memory cell means each memory cell has an address -1 -1 so end up -2 lah. So A -2. So find the answer here lah. So A -2, what is the result? You try. You can try afterward. So number 4, choose the best statement describing the difference between the instructions in 32-bit wide, and the instruction can process a 32-bit data. So okay, over here you need to read the questions carefully. So the first is referring to the instructions. Okay, instruction is 32-bit wide. Okay, the second is the instructions can process a 32-bit data. So one is the size of the instruction, another one is the size of the data. Okay, they are not the same thing, the data and the instructions. So okay, you choose which one referring the best, indicates the meaning given here. So let's you try to guess which answer is correct. A, the instruction is 32-bit wide, means the instructions when it is converted into the machine code, its length is 32-bit. Then B, the instruction can process 32-bit data, means the instruction can do operations for many types of data bit length. C, the instruction is 32-bit wide, means it can manipulate 32-bit data only. D, the instruction is 32-bit wide, means 2 memory locations are needed to store the instructions. E, no difference between both segments. So tell me, which one is actually indicating the meaning for the statement given. Okay, try to guess. A, B, C, D, E. Okay, hello class. Where's your answer? A, B, C, D, or E? Hello class.
B.
B. Okay, so one answer B. How about the others? Just guess.
B too. B.
Yeah, mostly B. So the answer is A. So the instruction is 32-bit wide, means instruction when it is converted into the machine code, the length is 32-bit. Okay, so this is instructions. Instructions 32-bit wide means the machine code is 32-bit wide. Okay, the instruction can process a 32-bit data, means the instruction only manipulate 32-bit data. I cannot manipulate the data at different lengths. Okay, so that is depends on the instructions. So when define instructions on 32-bit, it manipulate 32-bit data only. When define instructions manipulating 16-bit data, then it process 16-bit data only. Okay, it is not smart. Okay, like you define 32-bit, it can manipulate 8-bit, 16-bit, or 32. Okay, so human being can. Okay, when I tell you, like this, so some you manipulate in X, some like this, some like that, but machine is not. Machine is based on instructions. So 1 is 1, 2 is 2, 3 is 3. Okay, they never have in between. Okay, clear? So the answer is A. So we need to know, understand that, okay? Okay, what is instruction size? So the 32-bit wide is the instruction size. So let's proceed. Okay. Yeah. Okay, so based on the assembly program below, determine the content of memory address. Okay, this address after the program is executed. Okay, so this requires some analysis. Okay, push and pop. Okay, so if you look at here, okay, initially, okay, the step pointer, okay, is defined as this address. Okay, this is the top of the stack address. Okay, then, okay, LR R0 content initially configure this figure, this data. R1, okay, defined with this value. R2 initially contain this value. Okay. So based on determine the content of this after the program is executed. So the first is push. Okay, push R2. So the top of the step, okay, is this, right? Okay, so 130, okay, minus 4. Why is you need to use hexadecimal, okay, calculations. Okay, 130, so minus 4, so it's okay, FEDC. So it's so it start from the top of the step 0x200000130. Okay, then the okay next top of the step is a 0x okay 2000012 sorry 2 okay FEDC. Okay, then the following okay step top of the step is 12C. Okay, C B A 98. Okay, which is 0x200000128. Okay, 3 pop. Okay, 3 push and 3 pop. Okay, so okay, then the next okay, top of the step is 22012 okay 776 okay 54 124. Okay, so these are the okay, so initially okay the top of the stack is here. Okay, so this is the first. Okay, so when I execute, okay, this is a push R2, so that means okay the content, the data will be stored here. So the data will be arranged okay in 0x okay 11xx7766. Okay, so you need to remember lah, okay, how they are organized inside the inside the step. Okay, so this is in the okay a group of byte, okay, and then in the opposite okay organized order, okay, which is 11xx7766. Okay, then next is to push R1, so push this data, so they will be pushed into here. So okay, the data will be okay 6171 okay 81 and 91. Okay, then finally is to push okay R0. So R0 okay will push on top of this top of the step. Okay, so it's a 0x okay BB DD CC FF. Okay, so identify a content of the, this is the content of memory step. Okay, so this is the address top of the step for the step. Okay, and then determine the what is the memory address for 12C. So 12C is referring to this position, so it is the answer is B. Okay, so okay, it requires some okay, applications skill. You understand, okay, the operation of push, okay, how the data organized inside the step memory. So any question, class?
I want to ask some question, Doctor.
Yes.
Why do we jump straight to 1 to C for the address instead of 1 to F?
1 to C, why jump to 1 to C instead of 1 to A?
Yes.
So of course the address it will decrement in a decrement form. So start from 130. So 130 minus 1, what is the value? 130 minus 1 equal to
1 to F.
Then 1 to F minus 1 equal to
1 to E.
then minus 1 again.
1 to D.
Then minus 1 again.
1 to C.
Why is decrement by 4? Because every content here we show 4 byte. 1 byte require 1 memory cell or 1 address to store the data. So therefore here minus 4, and then the data we show 4 byte.
Okay, Doctor, understand.
So then the question is just to determine the content for this 200012C. So once you identify the content, then you need to identify where is the location for 12C. Then determine the data. This is the data. This is not address. 11 is the data. All right.
Okay, Doctor.
Okay. So I think this question is quite similar lah. So you need to try on, just you will get the idea. Okay. So this is to pop. So actually it's continue from here. So this question is based on the push. Okay, then after that I need to pop out, right? So pop. Okay, so what is the result? Okay, of R2. Determine the content R2 after the program. So okay, this is push, 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 okay, and then pop. So what is the content of R2? So this question is very easy lah. Just test your understanding. So try to guess. Okay, what is the result? What is the content after execute this sequence of instruction? This is a subroutine. So A, B, C, D, E. Okay, which one is the correct answer? This one no need analysis, one very simple one. Okay.
E.
B.
E.
Why B? Huh?
E.
E. Okay, answer is wrong. Okay, answer is C. Okay, if you look at here, the first is assign the label equal to this address, right? This parameter. Then following 4 instructions is to define initial value for SP R0, R1, R2. Then next push, push, push. When push, actually the content remain no change. There will be no change on the content. They will remain the initial value defined here. Then the port, the result port into the R3, there is no relations to R2. So that means the content of R2 no change. Remain the same. So this will be C is the result. Am I right?
Yes, so it will only change when we push it. The number is
Ah,
goes into
when
the
you
memory,
pop,
right?
when you pop into R2, then at that time the R2 will change. But now it pop into R3. It's not R2. So the question is asking you R2. So no change. Because the operation is not related to the R2. Even though there is a push, okay, just moving the data into the step, but R2 content remain no change. Okay, clear? So this is
Clear.
some tricky questions. So you must have a very clear mind. Okay, you need to think logically. Number 7, simple one. So this one, you already try in the quiz, right? So number 8 also simple one. Okay, there is some arithmetic operations. Then after that, try to determine the value for NZCV. Then I think we move 11. Try to identify the effective address for these instructions. So this is the instructions. What is the effective address? Do you recognize the addressing mode? Offset, post index, pre-index, which one? So what's the result? Effective address A, B, C, D, E.
B.
D. Any other answer? So who else want to try?
D.
Sorry?
D,
Sorry?
teacher.
D. Okay, wrong again. The answer is B. Okay. So effective address is based on the address information given inside the square bracket. And then this is the post index. Post index means after execute the instructions, the RM content, the register content will updated with the value, this value plus offset. But the effective address is equal to RM. To here. So we'll go back, try to look at the lateral nodes, the addressing modes post index. Question 12. So this question also very interesting. So it's a reverse engineering. The initial content of R0, R1, R2 are given. These are the initial content. Assume R0 is the destination register. After one of the operations below, so this is, if you look at here, some logical operation, right? AND operation, or this is AND for with the complement value. Complement operand 2. This is to multiply, right? This is to subtract. So after one of these operations, on the R1 and R2, R1 and R2 given these two values, which modify the content. okay, of R0. R0 is the destination, means okay, after the operations, the result will be stored inside the R0. Okay, so this is the result. So try to okay, relate okay, R1, R2, and R0. Okay, so R0 is the result. So what is the operation? So if you write the expressions, okay, they will be some kind like this. Okay, so R0 equals to okay, R1. Okay, there are some operation, but we don't know what kind of operation is it. You need to guess. So what operations it will result in this? Try to determine. Okay, what's the performance? Try to guess. So the result is 0, x, 1, 2, 3, 4, 5, 6, 7, 8. Okay. R1 in this case is 0, x, 0, 2, 0, 4, 0, 6, 0, 8. Okay, and then, okay, what is the operations between these? 0x, 1, 0, 3, 0, 5, 0, 7, 0. So try to guess what is this? So that okay, it will result in this. So anyone got an idea? What is it? Huh? Sorry?
Submit.
Sorry? A, B, C, D, E?
E.
E. Okay.
E.
So, okay. So one answer E. So any other
B.
answer? B. So any more? Any more? Okay. So need to analyze. Okay. So it seems like this value plus this value, right? So what is the operations that okay at the end it will give you okay equivalent to plus add like additions all right, so the answer is B. Okay, so far so good. So do you get, so normally in the exam the questions it will be vary, okay, many patterns, but it's to test your understanding. So you cannot okay just how to say memorize it. You need to okay to have a critical thinking, understand the concept, then after that you apply it. So that is the most important thing. Okay, when you do some self-study, you need to understand and then try to answer some of the questions so that you can deeply apply the concept. Okay, instead of just remember. When you remember, okay, when come to the solve problem, you don't know how to use it. But if you try to learn, okay, try to find some solutions, you start to thinking, and then you will start to think, okay, what is the principle, and then what should I know, okay, and then you will go to the identify, okay, the right, okay, content, okay, of the inside the lecture notes, and then study, okay, to find the solutions. So I think we go to the last questions. Okay, the rest I just leave it for you. You try yourself. Okay, we go to the part B. Okay, so questions 21. So listing Q21A show a simple okay, assembly program. So after the program is assembled, okay, the disassembly list okay, is given. Okay, so this is a original program. So okay, we can say this is like when the programmer, okay, write a program, okay, they will produce this kind of program. Okay, the line 1, 2, 3, okay, here, the line, the first column here is just some reference, okay, to indicate the line, okay, in later, okay, easy for you to refer, okay, where actually the instructions, okay, that we are talking about, okay. So, but the programmer normally, okay, they will write some program contain the column of label, mnemonics, and operands, okay. So the another program is known as a disassembly list. Okay, in the time microvision demonstrations, I got show you, right? Okay, after build process, okay, the assembler, it will generate the disassembly list. Inside the disassembly list, it provide additional informations, which is this the first column is the address informations. Okay, the second column is the opcode, machine code. So from the machine code, okay, we can know what is the instruction size. So just now remember, okay, there is a question. The instruction size is 32-bit. So this is a referring. This is we call it as the instruction size. Okay, so this is for the LDR.W, this instruction only. So the size is 32-bit. So if you look at this line, okay, this line. Here. Okay, so this machine code is a 16-bit only. Okay, so that means for the store, for these instructions, the size of the instruction is 16-bit wide. Okay, so not all the instruction has the size of 32-bit. Some of them 32-bit, some of them 16-bit. So because the ARM Cortex M3 implement time2 instructions. So time2 instruction is a combination of 32-bit or 16-bit instructions. So there is a meaning here lah. So that's why you get some this assembly list like this. Okay, and then this column, these two columns actually exactly same with what given here lah. But only the label, if you look at here, there is no label anymore. The label already replaced by the address. Okay, so if you refer here, this is a routine 1. This is the address for routine 1, which is referred to these locations to this point. So when execute, means the CPU, it will branch to these locations. So when you're going down, this program analyze, there's another branch instructions here. So in this case, this is actually branch to the routine 2. You can refer to the program here. First is branch to routine 1. So next BL instructions, it branch to the here. Branch to the routine 2 here. So which is referred to the address 13E. 13E, you come to this column is referred to this point. Then this is one subroutine. So inside here it contains there's a branch calling the subroutine again. So this is the address for the routine 3. This is referring as the starting address. 14E here. So if you look at this this program analyze it. It contains 3 subroutine. From here, maybe you don't get clearly the routines, subroutines organization, but in the original program, so if you look at here, it contains 3 subroutines. So the first subroutine, second subroutine, and third subroutine. And then this is the main body. Okay, so inside a main body, it call to the first subroutine. Okay, then in the routine 1, okay, there is a call to the routine 2. In the routine 2, there is a call to the routine 3. And then in the routine 3, there is no call anymore. So, okay, lastly, okay, there is a branch, okay, BX return, return to the routine 2 here. Okay, then over here it pop, okay, the value, return address from the step memory. Okay, in order to back to here, okay, then at this point, it will pop, okay, return address from the step memory, okay, into the main, okay, program, okay, to this point. But in this program, we don't have the address information. So we must refer to the this assembly list. Okay. So these are the, okay, the what are the basic understanding you must have, okay, when, okay, come to the this assembly list before you answer the questions. So let's look at the questions. So the first questions, give the value in the PC. Okay, when the microprocessor is executing the instruction in the line 3. So line 3 is referring to this. Okay, so this is the instructions. So over here, there is no information about the line, right? So in this case, okay, you can refer to the, okay, the first program. So line 3 is referring to here. So here, so means these instructions. So you can identify, okay, this instruction inside the this assembly list. Okay, because, okay, over here asking the program counter. So you need the address informations. So line 3 is referring to here. So this is a line 3. So again, we come back to the questions. So give the value of PC when the microprocessor execute the instruction in line 3. Okay, so when, okay, the CPU execute these instructions, we know that PC, okay, will point to the address of the next instruction, right? So what is the answer for PC? Okay, anyone can tell me? So this is a line 3. So line 3 is refer to the address 118. Okay. So when the CPU execute these instructions, PC point to where? So why take so long time? So the answer is in front UI. Hello? What is the answer? Excuse me. So anyone have idea what is the answer? Can you try to guess? Hello. Excuse me. So exam, okay, will be 散开 like this. Okay, there is no multiple choice questions. So you need to give some answer. No answer, no mark. So how is it, class? So your answer is just around here. So try to guess. So this is a question. What's the value of PC? Okay, when the microprocessor execute this line, this is referring to line 3. So what is the value of PC?
Is it 0x1000?
Sorry? 1 at
0x1000.
where is it? I don't see it.
At
So
the end of the assembly line of line 3.
yeah, this, you mean this? You mean this? The one have a underline, red underline. Okay, so in
I'm
this
not
case, you need to you must know what is the role of PC. PC is program counter. Okay, program counter, it will point to the instructions that will be executed by instructions by the CPU after that. Okay, so CPU will point to the next address of next instructions. Or you just remember CPU PC will point to the address of next instructions. Now CPU execute instruction at address 118. So means that the PC it will point to the address 11C. That is the answer. So the answer is so simple lah. Okay, you cannot answer because you have no idea what is the role for PC. So this is the provide address. Address of instruction. So when the PC CPU execute these instructions, this line 3 means this line. The next instruction is referring to BL.W, this instruction. So this is the answer. Okay, clear?
Clear, doctor.
Okay, B. Give the size of the instruction in line 8. Okay, so what is the size of the instructions? So explain the instructions and determine the value in the destination register after the instruction is executed. Okay, so here is write out the instructions. So if you don't refer to the this program inside the listing Q21, you can also finding the same instruction inside the listing Q22, this in this piece of program referring to here. Find subs. Here, only here, right? So ADDS here. Here, this line means ADDS. This is referring to line 7. Okay, so can you tell me what is the size of the instructions? Just now we already touched on the instruction size. So can you tell me where give you the size of instruction? Which column?
The second column.
So what is the size?
(16-bit).
So the size is referring to the machine code. Okay, so over here, every digit equivalent to 4 binary value. So it's representing 4. So you count how many digits here, multiply by 4. So that will give you the size. So in this case, the line 7, the machine code is 1842. So 1842, it contains 4 digits. 4 digits multiplied with 4. So equals to 16. So it means the size is 16-bit or half words. Then what is the meaning for ADDS? So this one you can refer to the instructions to get the explanations. And then after that, determine the result. So to find the result, you must know what is the value for R0, what is the value for R1. So you need to do the analysis. Like you need to find the previous instructions. Where is a line that define the value for R0 and R1? So if you look at the program, before the ADD, there's a move, right? So this instruction move 10 into R1. So, and then before that, there's another instructions to move 10. This is hexadecimal value, immediate value into R0. So, meaning that these two lines, is to initiate, the value for R0 and R1. So from here, you get know, what is the content for the R0 and R1. Then use this value, to perform the arithmetic operations. So this is the add operation. So the result will be stored inside R2. So give you result lah. So determine lah. But in these questions, if you read here, it don't mention specifically the destination register. R2, R0, or R1. So in this case, you must know which one represent the destination operand. So normally the first operand is dedicated for the destinations operand. So you must know lah, all this. So later you can try to answer lah, find answer for the B. C determine the value for LR and PC. LR is a return register. PC is a program counter. Of the microprocessor is execute the instruction in line 21. So now is going to the following line. So that means more analysis required. But the answer is just for LR and PC only. So the content for other register you can ignore. The most important analysis focusing on the subroutine, calling subroutine, and then the PC, the changes on the PC. So from the beginning until the line 21. Line 21, which is referring to the sub, R0, immediate value. So you can refer to a program here directly. I think it's this line here. You can also refer to the previous program, much more easier. is directly define line 21 here. This is a line 21. Before that, it is inside the routine 2 lah. Routine 2. So this is a routine 1, routine 2, routine 2 here. So sub. So here, sorry, it's over here. So line 21. Is inside. If you refer, analyze. This is the address for routine 1. So this is calling the routine 2. So this is to branch to the routine 3. So the line 21 is inside, appear inside the routine 2. So is these instructions. So which is referring to this. So meaning that there will be a call from the routine 1, right? From routine 1 here, there is a call to the routine 1. Routine 1 is over here. This is the address for the routine 1. So it call to routine 1. So inside the routine 1, it will start to execute the push, follow a move, sub, and then call the routine 2. So when you call the routine 2, the return address, which is this. This is this return address. And come to inside here, the return address is referred to here. So this is the return address. So that means, when we jump to the routine 2, routine 2 is a 13E. This is locate here, routine 2. So when at this point it jump to the 13E, but the PC supposedly point to this 13A. But since it jumped to the subroutine, so the 13A now become the return address. It will push into the LR register. But the actual value of the LR will be equals to 13A. Plus 1. So this value will store inside the LR. And then the PC it will start to point to here. So at that case, start from here and then to execute these instructions until this point. At this point, when the CPU execute this instruction, PC is supposedly pointing to 146. So that means the value for PC is 146. So LR value is 13B. So this one requires some analysis. You need to relate all the core relations and then try to identify the LR value and PC. So this will be the PC value. So PC value is 146. LR value is this figure 13A plus 1. So that is the answer for C. Clear?
Okay, Doctor.
Clear? Then D, draw the step and determine the value in it when the microprocessor is executing the line 22. So line 22, okay, so it's actually referring to here lah. So because just now we analyze, okay, up to line 21. So okay, we know that this is actually is the line 22. So line 22 is referred to this. Okay. So here. So you need to start from the beginning now. Okay, when call the subroutine, so it jump to the 12E. So at the point at 12E, there's a push. Okay, push of LR. So push of LR means okay, initially okay, the LR contain 121. So 121. Okay, so that is the first okay, routine one return address. Okay, return case which is 0000120. Okay, but the LR value is 120 plus 1. So that means okay, when it jump to 12E, so the LR value at this point, okay, the LR value is actually is LR equals to 0x1 000000121, okay, which is return address plus 1. So LR contain this. Okay, then after that, okay, inside this program, this is a subroutine. Okay, execute a move sub and then call the subroutine again. So when call the subroutine, okay, it will jump to the 13E. So before it jump to the 13E, supposedly is going to here, right? So that means there is a return address. So in this case, okay, the LR value that going to push into the step, okay, for this case is LR equals to 0x00000013B, which is 13A plus 1 equal to 13B. So this value will push into the step. Okay, then after that, inside here, it will okay, execute move sub okay, branch. Okay, so until when it is executing. So when you execute this, okay, and then it just jump to 14E lah. So there is no push anymore. So that means inside the step, okay, the step value is, what is the initial value for step? Okay, you go to here. So the initial value for step is this. So this is the top of the step. So the top of the step is start from 0x100000 to 00. Okay. Then after that, minus 4. Okay, to find the decrements top of the step. So 200 minus K4, then it result to 1000 okay 01 F E B C. Okay, so 200 minus 4. You can use a calculator, okay, to find this top of the step value. Okay, then after that, okay, 1FC minus 4 again, equivalence to 1, 0, 0, 0, 0. Okay, C, B, A, 9, 8. Okay, so 1, F, 8. Okay, so the data, the first, okay, this value will be pushed, okay, into the 1FC. So that means the content, okay, in the stack, okay, in these locations is 0x. Okay, remember, okay, the lower address to lower, okay, so the lower byte, okay, data. So which is 21, okay, then followed by 01, okay, 0000. Okay, and then, okay, next is to push this, okay, value into the step. Okay, so into the 1F8. So the result will be 0x, okay, 3B, 01, 0000. So these are the content, okay, for the, okay, step memory. So you need to sketch out lah. Okay, you can sketch, okay, and then show it some kind like this. Okay, some kind like this. Okay, because this is in the PDF form now, it's very hard for me to draw the line. So I just, okay, ignore the box, okay, that representing the memory. But this is the content now, so okay. So you need to, okay, perform some analysis before you able to determine the content of the step. All right. So hopefully through this example, you can gain some knowledge. Okay, what will come out, okay, in the finals. So if you are given some disassembly list, and then you know what are the informations available in assembly list. Okay, and then you must know, okay, to perform the analysis. Okay, and then you must learn. Okay, you must learn. There is no, okay, shortcut. Okay, then there's, even though I give you the answer, it's not necessarily guarantee you can answer in the final. Even though I give you a questions, okay, it is not guarantee you able to answer, okay, correctly in the final. Okay, if you don't, okay, understand the principle. Am I right?
Yes, doctor.
So any questions before I end these discussions? So any questions? So hopefully tonight's exposure, okay, you gain some knowledge, okay, you get some idea lah, and then, okay, it can help you to prepare well for the exam. Okay, thank you.
Thank you, Doctor.
Thank you, Doctor.